Let's take a look at continuity. Let me get my tablet going here. And we have a graph. Graph is going from left side from the right side here. And as it's going, there's no holes and there's no gaps. Well, you don't have any holes, you don't have any gaps. This is continuous everywhere in here. Now, specifically, the standard definition of continuity you can read in a book says that at a particular point here, that the function exists. It's defined. Well, that's true. Would be. And also, the limit as x approaches this value exists. Now, you can have a value existing at an x value, like you have it here, and then it continues up here. Well, it's defined here at this point, but the limit doesn't exist because coming from the left side and from the right side, they don't agree. Well, this is a hole. This is this is a gap in here. So this is an example of a gap. And then the last one is that the limit as x approaches c of f of x is equal to f of c. Well, we're going to look at where something's really discontinuous at. Now let's first look at the first problem here. It says determine whether the function is continuous on an entire real line. We got f of x is equal to x to the third minus 2 to the fifth power. Now, basically our trouble areas, and this is just the ones we'll run across in this section, is where you have fractions. Now, specifically where we have x's in the denominator, downstairs, where you have piecewise functions. Now, these are potential trouble areas. Doesn't mean they will be trouble. And where you have radicals. So for this one, where it says determine whether the function is continuous on an entire real line, if we don't have fractions, we don't have piecewise functions, and we don't have radicals, our three major trouble areas, then it's continuous everywhere, from negative infinity to positive infinity. So the question here is asking, determine whether the function is continuous on an entire real line. It is. It's continuous everywhere. Okay, let's look at a fraction now. So we got f of x is equal to 8 over x squared minus 1. Now we're going to approach this from the other side. Instead of looking at where it's continuous, we're going to look at where it's discontinuous. So when you have a fraction, actually let me erase that. This is for fractions. To find where it is discontinuous, set the denominator equal to 0 and solve. So to find out where it's discontinuous, set the denominator equal to 0 and solve. So we got x squared minus 1 equal to 0. Now you could use the square root property to solve this, or just factor it. I'll go ahead and factor it. This is the difference two squares. Factors as x plus 1 times x minus 1. Zero factor property says you get 0 on one side, you factor the other side, you're going to set each factor equal to 0. And we end up with negative 1 and positive 1. Now these are the areas where it's discontinuous. So for this problem, it's asking, determine whether a function is continuous on an entire real line. Well, we just found two areas where it's discontinuous. So the answer here is no. It's not continuous on the entire real line, because we found two places where it's discontinuous. Let me write that here. These are where it's discontinuous. Let's look at another problem. We got f of x is equal to 2x over x squared plus 5. Now our instructions say determine whether the function is continuous on an entire real line. You cannot just say just because it has a fraction that it's not continuous on an entire real line. Let's actually follow our steps that we outlined above and work this problem down. We said to find out where it's discontinuous, you set your denominator equal to 0 and solve it. So set x squared plus 5 equal to 0. Now this is the square root property. We'll take the 5 to the right side, becomes a negative 5. Square root property says you drop your squared and you put a plus or minus square root around the other side. Well, whenever we have a negative inside of our square root, that gives us an I. Now, i's really have no bearing at all in business calculus. So when this is saying that it's discontinuous at plus or minus I square root of 5, that actually means nothing in terms of discontinuities, which means this is continuous everywhere. This is continuous, and I know that's not an appropriate abbreviation, but I'm going to go with it. It's continuous from negative infinity to positive infinity. So the answer here would be yes, it is continuous on the entire real line. Well, let's take a look at some problems dealing more with this. So number 4. This says, describe the interval in which a function is continuous. If the function has a discontinuity, identify the conditions of continuity that are not satisfied. It's really easy to work these kind of backwards. We're going to find out where it's discontinuous at. Well, we've already talked about fractions. Set your denominator equal to 0. So I'll set x squared minus 9 equal to 0. And I'll factor this using the difference of 2 squares. So it factors as x plus 3 times x minus 3 equal to 0. Well, square root property says if you get 0 on one side and you factor the other side, you're going to set each factor equal to 0. So set x plus 3 equal to 0 and x minus 3 equal to 0. And we get negative 3 and positive 3 for our answers. Well, the question was, that's where it's discontinuous. But the main question was, where is it continuous at? So that's where it's discontinuous. Now where it's continuous at, you could write x is not equal to negative 3 and x is not equal to 3. A better way to write it, the match what the book does, is interval notation. This will go from negative infinity to negative 3, union, negative 3 to positive 3, union, 3 to positive infinity. And just shifting myself here, and got kind of tangled up in wires. There it goes. Okay, let me save this. There we go. And this will be BC continuity page 01. And let's look at our next problem. Okay, so we got f of x is equal to x to the third minus x squared plus 2. Well, we said our trouble areas were fractions, piecewise functions, and radicals. We don't have any trouble areas right here. So where it's asking where's it continuous at, describe the interval. It's continuous from negative infinity to positive infinity. So that's our answer. Now let's take a look at this one. We got f of x is equal to x minus 4 over x squared minus 6x plus 8. Okay, we got a fraction. To find out where it's discontinuous, which is what I'm assuming there, yeah, continuity, we set the denominator equal to 0 and solve it. So I'm going to set x squared minus 6x plus 8 equals 0. Now this is the PSD method. X squared, x, no x, and there's no number in front of your x squared. So this factors as x minus 4 times x minus 2 equals 0. Set each one of those equal to 0, so I set x minus 4 equal to 0, and x minus 2 is equal to 0. And we get x equals 4, and we get x is equal to 2. Now this is where it's discontinuous. Now to write where it's continuous at, a couple different ways. You could write x cannot equal to 4 and x cannot equal to 2. Or you could put an interval notation, going from negative infinity to 2, union, 2 to 4, union, 4 to positive infinity. And that'd be where it's continuous. Now let's take a look at the graph of this. And then I want to talk about why it's not a good thing to look at your graph to determine where it's discontinuous or continuous. So I press y equals, I press clear. Now to graph this, on your calculator, whenever you have more than a single term up on top or a single term on the bottom, you have to put parentheses on it. Well, there's 2 terms up on top, so I'll put parentheses on that. And there's 3 terms down here, so I'll put parentheses on that. Other than that, we're going to enter it as you see it. So I'll do a beginning parentheses, x minus 4, close parentheses, divided by, beginning parentheses, x squared, minus 6x, plus 8, and then closing parentheses, and then graph. Well, as I look at this, obviously we've got a problem here. Here's a gap. And that it looks like it occurs at x equals negative 2. Sorry. Well, that kind of makes sense. We said x equals 2. But if I look over here at x equals 4, it doesn't look like there's any kind of problem there. It looks like it's continuous. What actually is happening with this? I'm just sketching it. Calculator will give you a much better picture. Okay, it looks something like that. Use your imagination. There's a gap here too. Well, at 4, where we said there was another discontinuity, there's actually a hole in your graph. So there's an open dot there. Now, unfortunately, the calculator can't show that to us. So looking at the graph is not a very good way to tell where something's discontinuous or continuous. The book will kind of emphasize the look at the sketch, but again, I wouldn't rely on this. We'll go with algebraic techniques if we can. Now, sometimes you have to look at the graph, but if we at all possible can use algebra, we're going to focus on that. Okay, so let's look at our next problem. This is a piecewise function. Let's first talk about piecewise functions, then we'll look at this one. Piecewise functions. Now, coming from one side, it'll look like maybe something like that. And then come from the other side, it could look like this. Where it changes at, see how this is x is less than or equal to, and this is x is greater than 2? That's a changeover point. Maybe this would be 2 here. Now, these aren't the graphs of what you see over there, but let's pretend that we had something that looks like this. Well, obviously, we have a problem here. We have a gap, and we said gap indicates a discontinuity. Well, we could have another example where we have our line like that, and then the other one picks up where that one left off. And you see that there is no gap. Well, that's going to be our basis of what we're going to look at with these piecewise functions. So let's look at this one. We got f of x is equal to 8x minus 1 and 3x plus 9. And we got x is less than or equal to 2, and we got x is greater than 2. Okay. To finding discontinuities, hopefully I spelled that right. Discontinue. Obviously spelling's not my big now I'm more curious than anything if I can spell it. Annuities. There we go. Hopefully that's spelled right. We'll pretend it is if it isn't. Find the discontinuities in a piecewise function. Step 1. Look at each piece for our trouble areas. Now remember, our trouble areas were where we have a fraction, specifically with an x downstairs, where we have a radical, or where we have a piecewise function. Well, if I look at each individual piece, like 8x minus 1, that's just a line. Doesn't have any holes in it. There's no fractions, there's no radicals, so that's fine. 3x plus 9, there's no holes, nothing there, it's fine. Remember, it's only if you have a fraction or you have a radical. Now, you really can't have a piecewise function inside of a piecewise function, so that's nothing to worry about. So we're looking for radicals and fractions. You don't have either of them, then they're fine. So here, there's no discontinuities. Now, this is the changeover value, 2. When x is less than or equal to 2, it looks like this. When x is greater than 2, it looks like this. So we're going to plug in the changeover value into each piece. So we're going to plug in the changeover value into each piece and simplify. If they are equal. So if they are equal, there's no discontinuities at the changeover place. So no discontinuities at changeover value. If they are not equal, then it is discontinuous at that changeover value. Now we just up here in part 1 said that there's no discontinuities in each individual piece. Okay, well let's now plug in our changeover value, which is 2. It'll always be whatever number's right here. Let's plug that into both pieces and see what happens. So plug it into the 8x minus 1. We'll also plug it into the 3x plus 9. Well, I got 8 times 2 minus 1 gives me 16 minus 1, or 15. Here I got 3 times 2 plus 9 gives us 6 plus 9, or gives us 15. These are equal, so there's no discontinuity at x equals 2. Well, up on the first step, we said there's no discontinuities, and here we said there's no discontinuities where it changes over. So this is actually continuous everywhere, from negative infinity to positive infinity. Let me save this, and then let's look at another example. look at this one. F of x is equal to 9x and 9x minus 1, sorry, and x squared minus 2. This is x is greater than 3, and this is x is less than or equal to 3. Okay. The first thing we look for is discontinuities in each individual piece. 9x minus 1, that's a nice line. There's no fractions, no radicals, so we're okay. X squared minus 2, that's a nice parabola. There's no fractions, there's no radicals here. So in each individual piece, there's no discontinuities. Well, the question is, what's happening at 3? Are they meeting, or is there a gap there? Well, if I plug 3 into the first piece, I got 9x minus 1, and I also plug it into the x squared minus 2. Well, we got 9 times 3 minus 1 gives us 27 minus 1, or 26. If I plug in 3 here, I got 3 squared minus 2 gives us 9 minus 2, or gives us 7. These are not equal. Since they're not equal, that means we have a discontinuity at x equals 3. Now, if I wanted to write that in interval notation, that would go negative infinity to 3, union, 3 to positive infinity, and this is where it's continuous, which is what they're specifically asking. It says, describe the interval which function is continuous. And describing an interval, the best way, I think, in my opinion, is the interval notation. And it says the function has discontinuity, identify the conditions of continuity that are not satisfied. Well, where the piecewise function changes, goes from one piece to another. They're not the same. Yeah, let's take a look at square root. See how to handle that. Got f of x is equal to x times square root of x minus 2. Now when you have a radical, so for a radical, boy, I'm just having a lot of trouble writing tonight. Better go to bed, I think. Let's try it again. I actually do know how to spell, I just can't write. Okay, for a radical, to find out where it's continuous. So to find out where it is continuous, set what is under the radical greater than or equal to 0, and solve. Well, we take what's underneath the radical, the x minus 2, and we'll set it greater than or equal to 0. We'll take negative 2 over, and we get x is greater than or equal to 2. And this is where it's continuous. And if I want to write an interval notation, it'd be bracket 2, and then goes to positive infinity. So those would be where it's continuous. Sometimes it's easier to find where it's discontinuous, like in the case of fractions. Sometimes it's easier to find where it's continuous in the case of radicals. Now the next problems talk about removable and non-removable. Problem 10 here says discuss the continuity of the function on the closed interval. If there are any discontinuities, determine whether they are removable. Well, let me give you an example of this. That'll help explain this. We got f of x is equal to x minus 1 over x squared minus 1. Let me take my glasses off. Kind of bothered me. There we go. Or actually, I took them off to scratch my eye, but more information you want to know. Come over here. Well, remember what we said about discontinuities. Very easy. Set your denominator equal to 0 and solve. So I got x squared minus 1 is equal to 0. This factor is using the difference two squares. This would be x plus 1, x minus 1 equal to 0. Set each factor equal to 0. X plus 1 is equal to 0, and x minus 1 is equal to 0. and we get negative 1, and we get positive 1. Without a doubt, these are our discontinuities. So that goes without saying. Okay, now let's come back over to the original problem. And we're going to go ahead and factor the bottom part. This factors as x plus 1 times x minus 1. Now notice the x minus 1's are the same, aren't they? So we're going to cross them out. We're going to remove them. Well, what we're left with is 1 over x plus 1. Well, if I were to take the x plus 1 and set it equal to 0 at this point, and solve it, I would get x is equal to negative 1. Now look at that. This happens to match this one right here. X equals negative 1. And up here, x plus 1. Well, that matches what I said equal to 0 there here. So this right here is what's left. Now look what got removed. The x minus 1. Well, here is the x minus 1. This one got removed. So this one will be a removable discontinuity. Basically means it'll be a hole in your graph for this particular problem. Now, this one over on this side did not get removed. This is non-removable. Let me try it again. There we go. This one is non-removable. So very easy to tell which is which. Of course, you set your denominator equal to 0 to find your discontinuities, and then you put it back in fraction form, factoring it, and see what cancels. What cancels is called your removable discontinuities. Let me save this, and we'll take a look at some problems. There we go. So let's take a look at this one. We got f of x is equal to x over x minus 3 from 1 to 8. And it says discuss continuity. If there are any discontinuities, determine whether they are removable or not. Well, again, a fraction, the easiest way is to work it backwards. Find out where it's discontinuous. So we're going to set the denominator equal to 0 and solve it, and we get x is equal to 3. So again, without doubt, this is a discontinuity. I'm going to write down the continuous part here in a second. But remember, removable means I can factor the top and bottom and something can cancel. Well, there's nothing to factor here. There's nothing to cancel. So this is non-removable. Now, if I wanted to write out where it's continuous at in the interval notation, well, I could write x is not equal to 3 if I wanted to. That's one method. Or I could go from negative infinity to 3, union 3 to positive infinity. Well, let's look at our next example. Got f of x is equal to x plus 1 over x squared plus 10x plus 9 in the interval from negative 10 to 0. Okay, first thing, with a fraction, we set our denominator equal to 0 and solve it. So we got x squared plus 10x plus 9 equal to 0. This factors. This is the PSD method. X squared, x, no number for the x squared. So this factors as x plus 1 times x plus 9. Set each one of those equal to 0. It's zero factor property. And then solve them. And we get negative 1 and we get negative 9. Without a doubt, these are our discontinuities. Let's go back to our original problem. The bottom part factors as x plus 1 times x plus 9. Now you notice the x plus 1 and x plus 1 are the same, aren't they? The x plus 1's removed. The x plus 1's removed. Well, the x plus 1 ties directly to this right here. So x equals negative 1 is a removable discontinuity. Now then I got 1 over x plus 9. The x plus 9 remains. So this is remaining. So this x plus 9 here is going to be the non-removable. Well, where's continuous at now? We said it's discontinuous, negative 1, negative 9. So you could write x cannot equal to negative 1, x cannot equal to negative 9. If you want to put it into interval notation, it'd be from negative infinity to negative 9, union, negative 9 to negative 1, union, negative 1 to positive infinity. Now these next problems, oh, by the way, I didn't mention it, but see how I came up with negative 1 and negative 9? They both have to be in your interval here. So if one of them didn't fall in this interval, then we wouldn't even worry about that one. So they both have to be in this interval. I don't think they probably throw any trick questions in there like that, but just in case, you know how to handle it. These next problems imply they want you to do them with a calculator. We've already talked about how that's not good because you don't get all of your answers that way. So we're going to use algebraic methods to do this. So we got f of x is equal to 7x squared minus x over x minus 3. Well, remember what I said. If you got a fraction, set your denominator equal to 0, and that's where it's going to be discontinuous. So we'll set x minus 3 equal to 0, and we get x is equal to 3. So that's where it's discontinuous. Now it says sketch graph describe the interval in which function is continuous. Well, for our continuous, very short and dirty, you can write x cannot equal to 3. Or if you want to write an interval notation, it'd go from negative infinity to 3, union 3 to positive infinity. Now our last one. Again, we're going to do algebraic methods because it's best. So we got x squared plus 1, 3x plus 2. And a changeover point is x cannot equal to 0 and x is greater than 0. So it's going to be at 0. Remember our two steps for this. First step is to check each individual piece and see if it's continuous. Well, x squared plus 1, there's no fractions, no radicals. That's okay. 3x plus 2, there's no fractions, there's no radicals. So there is no discontinuities in each individual piece. Well, now we need to check our changeover point. We're going to plug in x equals 0 into both pieces. So we got x squared plus 1 and 3x plus 2. Now if I put 0 in here, I got 0 squared plus 1. 0 squared drops away, so that gives us 1. And if I put 0 in here, I got 3 times 0 plus 2, which gives us 2. They're not equal, are they? Well, that means we got a discontinuity at that place. So it's discontinuous at x is equal to 0, or changeover place. Now, if I want to write where it's continuous at, you could very quick and dirty write x cannot equal to 0. Or interval notation would be negative infinity to 0, union 0 to positive infinity. And that's actually the end of that section. So let me go ahead and save this. And it blew up on me, but that's okay because I'm done there. And then stop the recorder.